Okay, I'm going to do this in real time so that you can see my thought process. Take longer than it would for me to just go through and do it. And I'll talk about like all the conceptual questions here. When no work is done on a particle, kinetic energy is constant. That is true. That is the work energy theorem. The work energy theorem says the net work, all the works added up, equals the change in the kinetic energy. So if all the works added up equals zero, kinetic energy must not change. If a ball falls straight down, then there's only one force acting on it, and that is a conservative force, gravity, which means energy is conserved. Momentum is always conserved. And when we say energy, I mean mechanical energy. Total energy is always conserved too, but usually when we say energy is conserved, we're talking about mechanical energy. Friction always does negative work because friction always opposes slipping. So you're slipping in one direction, friction will point in the other direction. Remember, work is force times displacement and magnitude times the cosine of the angle between them. The angle will be 180 degrees. Another way to think about this, positive work means you're putting energy into the object. You're either increasing its kinetic energy, you're increasing its potential energy, its spring energy, you're giving it some kind of energy. Negative work means you're taking energy away from it. You're decreasing one of those. That's what friction does. It's decreasing kinetic energy. So it's negative work. If a heavy truck and a light truck have the same momentum, that means mass times velocity is the same. This one's actually tricky. This one's not straightforward. Okay, yeah, this one's a little tricky. Like I had to actually think about this. All right, so we'll have like one half, we'll have M1 V1 equals M2 V2. They have the same momentum. M1 is bigger than M2, so that means V1 must be smaller than V2. So I've got small times big equals big times small. Kinetic energy, I'd be putting a half in front of both of those. I know I'm not done. M2 V2. Okay, so all I've done is put a half in front. This guy's, so that wouldn't change. These would still be equal, right? If I just put a one half and a one half here, they would be equal. If I multiply this now by another V1, I'll have his kinetic energy. Now, if I multiply this guy by V2, I'm multiplying this guy by something bigger. V2 is bigger than V1. So this quantity must be bigger than this quantity because this much was the same in both sides. V2 is bigger than V1, so this kinetic energy 2 must be bigger than kinetic energy 1. So the lighter car would have more kinetic energy. That one was kind of tricky. Now going backwards, yeah, I think this would all flow backwards. If the light car and the heavy car have the same kinetic energy, then the heavier truck must have had a bigger mass. I would have to think through that. Yeah, we would have to work that out. Going backwards, if they had the same kinetic energy, who would have more momentum? I'm not sure that would be as straightforward. Gravitational potential energy can be chosen to be zero anywhere. That is true. Okay, here's the key. You want to draw out the energy diagram. Anytime you're dealing with the spring, draw out the energy diagram. So here's some negative A, here's positive A. I'm graphing the total, I'm graphing the potential energy. Here, this is U of X. I know it's hard to read through all the writing there. This is the potential energy, which equals 1/2 kx squared. I forgot the K. So a mass on a spring, here's x equals 0. It's going to go out here to some A, and it's going to go back here to some negative A from 0. Here's 0 here. So it's going to oscillate back and forth. We have the greatest potential energies on the ends because I'm stretched out. So that's here. That's my big potential energy. We come back to 0. We have no potential energy in the middle. And then as we compress, we gain potential energy again. See, I'm back up here. I have big potential energy. The total energy the entire time is equal to this height right here. Let me do this in a different color. So right here, this height is my total mechanical energy at any given time. So the difference between these two, at any point here, at any point x, this distance is my kinetic energy. Because mechanical energy is constant the whole time. We always have this much energy total. The black curve is how much potential I have at each location. The difference between those is my kinetic energy. So over here on the end, I've got no kinetic energy. The mass is bouncing back and forth. Over here at this end, it momentarily comes to a stop. There's no kinetic energy. There would be no space in between the blue and the black. Right here in the middle, you've got no potential energy. It's all kinetic. We would have this much kinetic energy. That's when you're moving the fastest. And you would be moving to the left there. You're coming in. Back here at the back, so now we're slowing down. We're completely compressed. We're back here. Now we have no kinetic energy. There's no distance in between the blue and the black. It's all potential. Then we start moving back the other direction again. So now we're gaining speed. We have positive velocity. We're losing potential and gaining kinetic. And again, we have the maximum kinetic right here in the middle. Maximum potential on the ends, maximum kinetic right here in the middle. And maximum kinetic means maximum speed. Okay, so at the equilibrium point, kinetic energy is the largest, potential energy is 0. All right, let me make sure I'm not paused here. Okay. Forces that can store energy in a potential function are conservative forces, and gravity is always a conservative force. These two are never conservative. As we talked, in some weird cases, tension can be conservative, but it's not always. So you got a block pushing across a frictionless surface with a constant force. So see, I almost didn't read that. We got to be careful here. So we're pushing on it. Its kinetic energy will increase. because we're pushing on it from the side. And there's no friction, there's nothing that's going to slow us down. It would increase without bound if we kept pushing on it forever. This is true. In elastic, that's always going to sound weird. For elastic collisions, kinetic energy is conserved. For inelastic collisions, kinetic energy is not conserved. Momentum is always conserved. So a child's running, they jump on a stationary sled. This guy's momentum is zero at the moment, by the way. That child is going to lose some of their kinetic energy because they have to transfer some of theirs into the sled to get it moving. Kinetic energy will not be conserved. The total momentum, see, this is not worded perfectly. When we say momentum, do we mean the momentum of the child or the total momentum of our entire system? Total momentum of the system is always conserved, always. In this case, since this guy's momentum was zero, all the momentum of the child is going to be conserved. This is a perfectly inelastic collision because the kid's going to stick to the sled. So not only is the total momentum conserved because it always is, but the momentum of the child is going to be conserved. Um, oh no, see, that's not true. Nope. Okay, so now we do need to think about this. So we got M child V child plus M sled V sled, which is zero, must be, now they're sticking together, M child plus MS times V combined. This is all zero. This will equal this. So it is true that the total momentum of the child will equal the total momentum of them combined. That is true. It will not have the same velocity, though. This velocity will not be that velocity because now we've got a bigger mass. Okay. I just had to work through it and make sure. If the total work is positive, V must be increasing. Why? Because you're adding energy into the system. And we're talking about the total work here. Remember the network work total is the change in the kinetic energy. So this means if this is positive, kinetic energy final must be bigger than kinetic energy initial. Okay, now you got to be careful with this. This does not say if you're doing work on something, you're always increasing its kinetic energy. That does not say that positive work implies speed goes up. If I lift a book up at constant speed, I'm still doing work. I am personally doing work. I'm pushing straight up. It's moving straight up. But I'm doing it at constant speed. So I would not be increasing its speed. I would not be increasing its kinetic energy. I would be increasing its potential energy. But in that scenario, I was only talking about how much work I was doing. At that same moment, gravity would be doing negative work because gravity points down, the book is moving up. The total work on the book would be zero because I'm pushing up, gravity's pushing down, those works will cancel out. The total work would be zero, so its kinetic energy change would be zero. So you got to be careful here. Don't get it in your head that if you're doing positive work, you're increasing speed. That's not the case. If the total work is positive, then you're absolutely increasing the speed because you're increasing the kinetic energy. At the maximum point, kinetic energy is zero. Velocity is zero, so momentum is also zero. Potential energy is not necessarily a maximum. You can call anywhere you want. You can call the top potential energy equals negative 1,000. You can call it zero. You can call it anywhere you want zero. With a mass on a spring, we have a 0 point right here. That one's picked for us for potential energy. Gravitational potential energy, you get to pick anywhere you want to be zero. If a question ever says the gravitational potential energy is at a maximum, that no. Gravitational potential energy is at a maximum at infinity when you're infinitely far away. Or it's this one. This is a true statement. That's the definition of perfectly elastic. Kinetic and momentum are conserved. Momentum's always conserved. Kinetic energy is conserved in perfectly elastic collisions. I got to think about this one. This is not a very well worded question. If I'm going up an incline here, so if I'm going from here to here, the work I have to put in is the same amount of work as just lifting the thing up if there's no friction. If there's friction on here, I got to do extra work. I have to do this amount of work here, MGH, to get it that high, and I have to do work to overcome friction. So we would need both of these. We must be assuming here no friction. I'm going to make the assumption that that's what was meant by this question. Hey, I'm curious what ChatGPT says because it wrote the question. What one was that? Yeah, basically it said the same thing. It wrote the question, and then it's like, well, yeah, plus friction if it's present. It basically said this. That's nice. It said the same thing I did. Okay. And this is a good kind of question. I like this. Everybody falls at the same rate. Everybody will have the same velocity at the ground. So call these guys like A and B. VA is going to equal VB when they hit the ground. That's just basic kinematics. The masses cancel out. Like it, or we can look at it as conservation of energy. 1/2 MA, say VA squared would equal mgh, technically negative, but in absolute value, because it's losing this and gaining this. In absolute value, these will be equal. The m's cancel out. The velocity does not depend on the mass. Okay, now if the question said who has more momentum, if they have the same speed, this guy's going to have more momentum. So the answer would be same speed. Like we know that from kinematics. Joule is a Newton meter. Kilograms times meters per second squared, that's just a Newton. This is, nobody is that thing. I guess, like, what would that be? This would be a Newton per second. So force per unit time, that'd be something weird. Okay. So it's initial. Here's the best way to do these problems. Call it V1 squared. Here's his initial kinetic energy. Now here's number 2. I'm going to triple this. So 1/2 3V1 squared. Square both of those. I'm going to get 1/2 m times 9 V1 squared. Then I'm going to move this 9 in front. That right there was this. So we get 9 times the initial kinetic energy. We get 9 times greater. Or, like, you could have just worked this out in your head. Kinetic energy goes like V squared. If you make the velocity 3 times bigger, you can get 9 times the energy. If you make the velocity half, you'll get 1/4 the original kinetic energy. Negative work does mean the force is opposite of displacement. The component of force parallel to displacement. Okay, so 2 ice skaters are standing in the middle of a rink. They have no kinetic energy. Then they start moving, suddenly they have kinetic energy. Kinetic energy is clearly not conserved. Momentum's always conserved. Because remember, momentum is a vector. Energy is not a vector. That looks ugly, I'm going to say. All right, write that. That one true? Is that what that was? So they started with 0 momentum. They're going to end with 0 momentum. Because one will have positive and the other will have negative momentum. Not necessarily, oh yeah, they would have to be the same in magnitude. At maximum displacement, so we talked about that up here, talking about mass on a spring. So over here, kinetic energy is 0. Kinetic energy is biggest here when there's no potential. Remember, the black graph is the potential. The total energy is the blue line. So like right here, you got very little kinetic, no kinetic, maximum kinetic. Over here, 0 kinetic, 0 speed. 0 meters per second. Okay. All right, let's do some problems. Okay, So if I'm reading the question correctly, we got our guy here, and he's pulling this rope like this at a 30-degree angle. So what he's going to end up doing is he's reducing the vertical component of this tension is going to reduce the weight a little bit, which will then reduce the normal force a little bit, which will then reduce friction a little bit. And the horizontal component is going to be fighting friction and dragging him across the floor. All right, so free body diagram here. We've got the weight. Maybe I'll call that FG since we're going to have work in here. That's not a 6, that's a G. We've got the normal force. We know those are kind of going to be equal and opposite, but not quite because we're going to have another vertical component in here. We're going to have friction. We do have friction in this, right? Yeah. Some kinetic friction pointing backwards. And we've got some tension force here at a 30-degree angle. All right, so that tension force, 30-degree angle, here's tension. We're trying to find the tension. So here's my Y component, here's my X component. Some of the forces in the X direction will be Fk, which we know is a negative, so I'm just writing that as a vector, plus Tx, which will be positive. We can see that from the picture. That'd be mass times acceleration in the X direction. Some of the forces in the Y direction will be Fg. I'll write it as a vector for now. Plus the normal force, plus the Y component. These two are positive, that one will be negative, and this will be 0 because we're not accelerating up and down. And we're going at constant speed. Okay, I just now read that. Constant speed. So this acceleration is also 0. Okay, otherwise this is going to be a really hard problem. I was looking for more information there. Okay, so that tells me we're going to have a system of equations here. That frictional force we know is mu k times magnitude of the normal force. Trying to decide if I want to solve this guy or this guy first. Okay, I think we can go ahead and do this because remember, this is a negative. When I move it to the other side, we'll have Tx will equal the positive version of this where it's absolute value. So this is just Tx. Okay, and then over here, we get negative mg plus magnitude of the normal force plus Ty must equal 0. Yeah, we're going to solve this system. All right, Tx is magnitude of t. We can see from our picture here, cosine of theta. Ty is magnitude of t. I'll draw that t a little better there. Cosine of theta. Ty magnitude of t sine theta. That's just here from the picture. Okay, so we're going to have a system of equations with n and t in them. So this will be mu k times n. I'm just going to write n now to mean I'm not putting a vector on it, so you know that means magnitude of n. And I'm going to write t here for magnitude of t. Cosine of 30 degrees and negative mg n plus t sine of 30 equals 0. Sine of 30 is a half. Cosine of 30 is root 3 over 2. We could get our calculator out. So this implies mu k times n is root 3 over 2 times t. And this one says negative mgn plus 1/2, or t over 2, equals 0. Oh, I guess we'll solve this guy for t. So that will be mu k over n times 2 over root 3. I think that's going to be the easiest way, because when I plug that in here, we'll cancel out the t's. So this will imply, let's go ahead and move this guy to the other side. So I'm doing two steps here. I'm taking this and plugging it right here into t, and I'm moving this to the other side. So mu k n times 2 over root 3 over 2, so those 2's are going to cancel, will equal mg. So that says to me mu k n over root 3 equals mg. So n will be mg over, I guess we'll get the root 3 on top, huh? Root 3 mg over mu k. All right, now I can plug that in here. T will be mu k times n to mg, twice the weight. Maybe because we do have a 30-degree angle there. I'm really surprised that mu k divided out. Hold on, let me make sure I haven't made a mistake here before I go any further. Yeah, that answer didn't make any sense, and it's right here. Right here, when I was solving the system of equations, I forgot to write down that plus sign right there. So we need to go all the way back. Sometimes you do that and you get an answer and you're like, that answer doesn't make any sense. So you go back and you find your mistake. It was right here. That's a plus in plus t sine of theta 30 equals 0. Okay. So again, cosine of 30 is root 3 over 2. We could just keep the sine and cosine in until the end, but maybe it'll be easier to carry that along. And then right here, negative mg plus n, not times n. Like I should have caught that, mg times n. You're never going to get something like that. Plus t over 2 equals 0. Okay, so same substitution here. This is still going to be t equals what? Mu k n times 2 over root 3. Take that and plug that right there. So negative mg plus n plus 2 over root 3 mu k n, and then I've got this over 2. And that's supposed to equal 0. Let's make sure I got everything. So I got a mu k into root 3. This 2 right there is right there. Those cancel out. Okay, so this says negative mg plus n plus, that's mu k over root 3 n equals 0. Okay, so these are like terms. I could factor an n out of these two and move the mg to the other side. Let me write that so it's a little easier for you to read. That says mu k over root 3. And that's 1 plus that, because I'm factoring the n out of these two. That will equal mg. So now just divide over. N will be mg divided by 1 plus mu k over root 3. All right, plugging in all of our numbers. M was 25 times 9.8 over 1 plus mu k was 0.28. All right, let's hope this answer comes out reasonable. Here, I'll let you watch me type that into the calculator. Skip ahead for a moment if you want to watch me type that in. But people will type this in wrong sometimes. I want to divide by that whole thing in parentheses. It didn't type the parentheses. 25 times 9.8 divided by parent. There we go. 1 plus 0.28 divided by square root of 3. Get out of the square root. So I hit over, close the parentheses, to 10.9. Let me pause and see if that's right. That's what Chat GPT got. It's right there where the gate N is right there. Yeah, 210.91. Okay. Now, this is not our ultimate goal. We're nowhere near done. Newtons. All right, now T is going to be that times mu k divided by, or times 2 divided by root 3. So this will be mu k times n times 2 over root 3. Is there anything else in there? No, I don't think so. All right, so my calculator is smart. I can take that times 0.28 times 2 divided by square root of 3. 68. And as a sanity check here, 68.2. Look at that. Either we are smart or Chat GPT is smart. What was that, 0.2? Yeah, close enough. Newtons. Okay, that's still not what the question asked for. That was the tension. So that was really a test 1 kind of problem. We could have put that on test 1. Now, how much work is the rope doing? So we're moving this way, right here. Tension's pulling up that way. We're not pulling in the same exact direction as displacement. My displacement was 6 meters, by the way. So work is going to be the magnitude of the tension times the distance traveled, absolute value of displacement, times cosine of the angle between them. So 68.2 times displacement, that was 6, times cosine of 30 degrees. So times, I don't know what it just did there. I got to clear that. I wanted times, it was doing like an exponent or something. Times 6 times cosine of 30. You know, I don't know if I'm in degree mode. I gotta check my mode. I am. Okay. Make sure you're in degree mode. I could have just done root 3 over 2. 354.32 joules. So, yeah, kind of a long, involved problem. And you saw, like, I goofed in the middle when I got an answer that didn't really make sense. But totally doable. I mean, it's all stuff we've done before. All right, I'm going to pause and read this question. Okay, I think I'll do this problem two different ways. I'm going to do it the easy way, and then I'll go through work energy theorem and find all the forces and all the works and blah, blah, blah. I'll do it the harder way. And if you want, just skip over the harder way because there's an easy way to do this problem. All right, so I'm just going to separate this out. So we've got some slope here, and then it levels off. Up here, we're going to have some potential energy. If I call down here potential equals 0, my potential will be mgh up here. That's all converted into kinetic right here. So this initial potential will equal this final kinetic. Because there's no kinetic up here, there's no potential down here. Just conservation of mechanical energy. Then here at the end, over this region, we're going to do some work so that my final kinetic equals 0 and my final potential equals 0. And what is that work? That is the force times the displacement. But we know what that force is. We draw a free body diagram. We got the weight. I don't want to use WFG down. Normal force up. Those will be equal and opposite. We'll have some frictional force back here. That's an FK. And frictional force is mu times N, but N will be mg. So the work will be mu k mg times the distance, d, this distance here. Yeah, I think that's it. That distance is 25 there. This height here is 12. So 12 up there, 25 over here. And honestly, I don't even think we have to find the kinetic energy here because this energy that we're starting with, mgh, is all being dissipated by the end. We could, I was about to say, if they asked us to find the speed at the bottom, we could find the speed at the bottom. They did ask that. But I'm not even going to find that first. I'm going to find, and I lied to you. I lied to you. The total length here is 25. We're not going to make it all the way to the end. See here, length is 25, but they ask how far does he travel? So we must not make it to the end. Okay, it helps to actually read the whole question. All right, so this energy here, it gets converted all into kinetic, but it's still the same amount of energy. And then by the work energy theorem, all that kinetic energy is lost by the only force that's doing any work here. In this region, these two guys aren't doing work. We're moving to the right. These guys are perpendicular to displacement. They do no work. He's doing all the work. So what that means is mgh equals mu k mgd, and it will also equal 1/2 mv squared. When I say v here, I mean right there. And all the m's cancel out. We don't need the m. All right, so we could solve for d here. Heck, even here, just from these two, d will cancel out. GH will be mu k GD. G's cancel out. So D will be what? H over mu? What's H? 12 over 0.10? Wait a minute, that seems like that's going to be further than 25. Then why did they tell us it was only 25 at 120 meters? Oh, again, it helps to read the question correctly. This is not 25. This is D. Let me erase that. They meant that this length is 25. We didn't, who cares about that length? That length didn't play any role whatsoever. So this is not 25. When they said 25, they meant this side over here. Oh God, now I'm on the wrong one. 25. Um, yeah, who cares? We don't need that at all. If we, I guess over here when I'm doing it the hard way, yeah, yeah, we would have to use that. I don't even think I want to do it the hard way. Okay. Anyways, back to this. Now we need to find V. So we have this equation. The m's canceled. We have mu k times g times that distance we just found equals 1/2 b1 squared, or that just equals gh. Either one of those should give us the same thing. I'll use these and say v1 squared equals 2gh. So v1 is the square root of 2gh. And so just throwing that in, square root of 2 times 9.8 times, what was our height? 12. 1534. All right. And out of curiosity, let's see. Yep, exactly the same. And like did it exactly the same way I did. Again, we could have done this by finding all the forces on here, finding all the different works, because in this section here, when we're going down, gravity is the one doing work, but gravity's pushing straight down. So we would have to do mg times the distance, 25, times, and then we'd have to figure out the angle in here. That's where we could use the 25 to figure out this angle. And let's see, the horizontal component would be the sine of that angle. But you know what we would end up getting? MGH. That's what we would end up getting. It would just end up being the force times 12, because that's the vertical component of the force. Okay. Okay. Very similar problem here. So we're going down a ramp and then we're going to run into a spring. So we've got some mass up here. It's going to slide down and compress this spring. Conservation of energy here. So we're going to have some potential up here. We're going to have some kinetic right here. And then let's call this gravitational potential. And then we're going to compress this spring so much and have spring potential. But it's the same amount of energy everywhere. This guy is mgh. This one is 1/2 mv squared. This one is 1/2 k x squared. We don't have any friction anywhere. We don't have anything that's going to be robbing us of energy. The exact same amount of energy the entire time. We're just changing forms. So we can, again, do this all together or one at a time. So we're going to have mgh, my initial potential energy, equals the kinetic energy right here, right before we hit the spring. Again, I didn't specify it, but I'm assuming that right here is potential equals 0. I didn't have to do that. I could have called this potential equals 10. Then this change in potential would still be mg times this height. And that's all converted into kinetic, which then gets all converted into spring potential. And then we're stopping our clock once the mass is completely compressed. What would happen in this ideal case, by the way, that spring would then push the mass backwards. And right there, when the spring lets go, we'd have the same speed again. We'd just be going in the opposite direction. And then we would just go back up the hill to exactly the same spot. And it would just keep going on forever if there were no friction. You just compress, bounce back up, compress, bounce back up, keeping the same amount of total energy the entire time. Okay, like this is really just plug and chug now. Like here, maybe we'll just check and see. So there's our kinetic energy, mgh. All of that gets converted in, and we're solving for x, 0.384. Everything looks right there to me. You guys can I have no idea what this diagram is, though. That diagram doesn't make any sense. It gets confused sometimes drawing these pictures. But check the numbers and make sure that when you type that in, you actually get that. Like, I guess for completeness. Let me make sure I am recording. Okay. I've done this before where I've gotten this far into a video and realized I'm not even recording and I have to go back and re-record a bunch. All right. So you can skip over this if you want, but I am going to check these calculations. Times 1.5. What was 1.5? The height? Okay. Yep. And then square root. So we're solving for x there. The 2 will come up. The little k will come down. Yeah. So by big K there, they mean this kinetic energy they just found. Times, you can do this second answer to just put that in here. Divided by, and what was my K? 400. At 0.38, so 29.4. Joules, don't forget your units. And then X is the amount compressed. Obviously, I would want to see you write out some of these steps there, 0.38-ish meters. You got to be careful on spring problems because sometimes they'll give you the K in newtons per centimeter, or sometimes they'll ask how far in centimeters do we compress? And you would have converted that to 38 centimeters, but here they didn't. All right, are we almost done? Oh, wow, I still have 3 more. Okay, go ahead and read the question here. Hopefully you've already worked these out on your own. All right, this is the easiest of all the collision problems. This is a perfectly inelastic collision problem. We know that because they stick together. We will have always conservation of momentum in a collision problem. We do not have conservation of energy unless we're perfectly elastic. All right, so let's draw these guys out. I'm going to assume here's number one. I'm going to call this guy A and this guy B. And to the right, the other to the left. Okay, so VA1 equals 3, VB1 equals -2, MA is 1.5. Oh, they're both 1.5 kilograms. This is meters per second. Okay. Then, so this is before, this is time one. Time two, this guy's going to win because he has more momentum. These two multiplied together are bigger than these two. So now we're going to have AB together moving this way. And my final mass, maybe call it capital M, will be the combined masses because they stuck together. And we'll have some V2 that's going that way. Now, you could absolutely just memorize the formula. Like, I've never bothered. But in a perfectly inelastic collision, you have MA VA plus MB VB equals MA plus MB times V, let's call it just V2, like I did here. And this is who we're trying to solve for. I mean, it's literally always the same. I don't have this memorized because it's this easy to come up with. Like on your equation sheet, I don't even bother putting this on the formula sheet, even though it's a formula given in the book, because I mean, how easy was that? It's always the same problem. So now it's just plug and chug. All right, so like I'll put the numbers in here. This would be 3 times 1.5 minus, because that guy's negative, 2 times 1.5 divided by the sum of their masses. 1.5 plus 1.5 is 3. So that's 1.5 over 3. I think we get 1/2. I think that's 0.5. Yeah, meters per second. Like if you couldn't do that in your head, just type it in your calculator. All right, then fraction of the initial kinetic energy that's lost. Here we're going to have to do some calculations. I might make this a little bit smaller so that I got more space. Okay, there we go. All right, so we're going to have, there's my initial before the collision, 1/2 mv1 or MA VA1 squared plus 1/2 MB VB1 squared. This is how much kinetic energy I had to begin with. 2, I'm going to have 1/2 capital M, the total mass, MA plus MB V2 squared. This is how much kinetic energy I have at the end. This is beforehand when they're both moving. Both of these are going to be positive. Remember, even when I square this V, this is going to be a positive. This is the combined kinetic energy because they're one combined mass now afterwards. This number is going to be bigger than this number. So we're going to subtract all of this minus that to see how much we lost to deformation, making these things stick together because they literally plastically deform. Maybe we're breaking stuff, we're creating sound, we're creating heat, we're breaking chemical bonds. Total energy is conserved, but we have no way of tracking where that other energy went to. What we're tracking here is what happened to the kinetic energy. All right, and then it's literally just plug and chug. Like I don't know if you need to watch me. Okay, so here were the energies. There's the final. So we lost. Does it ask for fraction lost? I'm never going to ask you for fraction lost because what are we dividing by? People are going to goof on that. If you ask for what fraction was lost, they're going to divide by the final instead of dividing by the initial. That's not the way it works. You're supposed to divide by the initial. All right. So the energy loss was 9.38 joules. This was all I would ask for. Lost was at 9.38 joules. Again, assuming that ChatGPT typed all these numbers in the calculator correctly. So you go through, you check all that yourself. Okay, I like these questions a lot, like a lot. All right, how long have I got? I got a half an hour. I can get through two more problems. Okay, so I've got some block over here. I've got some arrow. So I'm trying to draw a bow and arrow here being shot out with some initial velocity. That's going to come over here. That's going to hit the block and stick to the block. And these together are going to slide some distance d. We're going to need conservation of energy and conservation of momentum here. Now we're assuming that this arrow is moving quickly enough that there's not much of a change in potential energy. So technically the arrow would come down and some of his kinetic is converted into potential, which will not get transferred into the block. We're ignoring that. Okay, so we're saying here the whole time my velocity is 60 meters per second because it's going to happen so quickly, we're not going to lose much to potential. So right here, the kinetic energy, right before it hits, the kinetic energy of the arrow will be 1/2 times its mass times its velocity squared. That's a 60 there. All right, so let's throw that in the calculator. $36. Is that a reasonable number? Yeah, I think so. So we've got 36 joules of energy. But this one's a little tricky. We're not going to, I just went through his calculation for nothing. We don't need that. Not all of that kinetic energy is going to get transferred into the block. The arrow is going to stick into the block. That's how much energy we had. Some of that energy is going to get lost, making the arrow stick into the block. Some of that energy is going to get lost to heat, to sound. It's going to make a whack, right? Imagine an arrow hitting a block. It's going to make a sound. We lost some kinetic energy. What we're going to have is conservation of momentum. So mg arrow will equal the combined. This is a perfectly inelastic collision because they're sticking together. Mv arrow. The initial momentum of the arrow will equal the combined mass times the combined velocity. This is where people mess up on this one. They don't have the combined mass here. They just think, oh, the arrow's momentum all gets transferred into the block. No, it gets transferred into the block plus arrow. Okay, so we will not need this. Didn't hurt that we calculated, but we won't use it. All right, so, and you might be wondering, wait a minute, what about the initial momentum of the block? Block was sitting still, it had zero momentum. So V combined will be MA VA over the combined mass. All right, what do we got there? Mass of the arrow, 0.2 kilograms. I'm going to need parentheses on the bottom, I think, only. 0.2 times 60 was his initial speed, divided by the combined mass, 2 kilograms plus another 0.02. So 2.02, 5.94 meters per second. Okay, now all of that kinetic energy, so the kinetic energy of the combined, this is the block and the arrow, will be 1/2 times his mass times that new velocity squared. All right, so I'm going to take that thing and square it. And then I'm going to multiply that by the combined mass, 2.02 times 1/2. So divided by 2. 3564. That's my kinetic energy. That's in joules. This is energy. Why did I calculate that? By the way, look, I'm glad I calculated that initial kinetic energy of the arrow when it left over here. We lost a little bit through sound and heat and plastic deformation and whatnot. All of this now kinetic energy of the combined mass block is going to get lost to friction. So we know what that frictional force will be. If we draw a free body diagram, we'll have the weight going down, the normal force going up, the frictional force, the kinetic frictional force pointing backwards. And we know in magnitude, this would be magnitude of the normal force. Some of the forces in the y direction is 0 because we're not accelerating up and down. So this would be mu k times mg. And then the work is going to be negative because this is a negative force. So let's say the absolute value of the work is going to be the force times the distance. That's what we're looking for, right? How far will it go? We want that distance. That amount of work is going to suck out all this kinetic energy that we just found right here. So the distance will be that number we just found, 64 divided by mu k times mg. Okay, we got to be really careful here. So I'm going to take that, put in parentheses, and multiply all three of these together in parentheses. Mu was 0.4. The total mass here, 2.02, I think is what I had, right? Yeah. And then G times 9.8. 4.5 meters. Well, that block's going to go pretty far. I'm a little concerned about that answer. Let me check. 4.5 centimeters. So this, I was off by a factor of 100 on. Where did I goof there? I'm just trying to figure out what I typed in wrong. Point. Oh, that should have been 0.02. Every time I had a 0.2 right there, that should have been 0.02. Okay. Yeah, I thought that speed was kind of big, but I didn't realize completely until I got here. There's no way that block's going to go. I mean, that's like 15 feet or something. All right, so let me go through and fix these. You don't have to watch that. Yeah, you probably noticed when right there is when I typed in 0.2 instead of 0.02. I'm not re-recording this. All right, let me pause so you don't have to watch that. Okay, fixed them all. Even had a 0.02 there. Always think about your answers. If your answer seems unrealistic, it's possible you did some small goof like that. Okay, and then this one's going to be the easiest. Like it looks the hardest, but it's not. All right, so the horizontal and velocity components of speed. Don't really even care about that. To answer these two, we don't need to do part A, but we're going to do part A because I asked us to. So 20 degrees above the horizontal, we've got some velocity vector V. Let me draw him a little bigger so that it will show up better here. This is 20 degrees. Here's Vy. Here's Vx. Here's magnitude of V. And this is 4. So it's just trig. Vx will be magnitude of V cos of 20. Vy magnitude V sine of 20. All right, those are whatever they are. Find the speed just before hitting the water. We're on a 5-meter platform, and we come over here. So it's call that T1. So you can type those in the calculator on your own. I'll show you the answers in a second. Don't need either of those. Excuse me, we could do this using kinematics, by the way. We had a problem literally like this on test one. Absolutely, we could do kinematics. Conservation of energy is so much easier. At first, I have some potential and some kinetic. Over here, I'm just going to have kinetic. Why? Because I am deciding at this moment to make P equals 0 right here at Y equals 0. Then my P1 plus K1, which only depends on speed, doesn't care about the angle. Oh, okay. I guess let's call these zeros if I already called that one 1. P0 plus K0 all gets transferred into K1. So I'm actually going to solve C and then go backwards and solve B. All right, this is MGH plus 1/2 MV0 squared will equal 1/2 MV1 squared. All the M's cancel out, and we'll get GH plus 1/2 V naught squared. I guess I'll just leave everything here. V1 squared. And then here, just for completeness, I got a couple minutes, might as well work this all out. 75 times 9.8. It was 5, right? Times 5 plus 1/2. Oh, no, the M's canceled. Oh my God. I almost goofed there. You guys almost let me goof. Nobody stopped me. I know you're not here to stop me. Heck, I don't even know if you're watching. The M's canceled there. I don't need that. I noticed when I got here, I'm like, hey, I don't have an M there. Oh, yeah, I canceled the M's. 9.8 times 5 plus 1/2. What was my initial speed? 4. So times 4 squared equals 1/2 V1 squared. So like I guess I would just type all this in the calculator, multiply it by 2, take the square root. 9.8 times 5 plus, and then I would just do this in my head. 16, half of that is 8 times 2, take the square root, second square root, second answer, 1067, 1068 meters per second. Let's make sure that's reasonable. We're falling 5 meters. Six meters per second. It seems a little big to me. Here's a way we could check it. Because that seems a little big. And yes, I know I could just go check chat GPT. I'm going to find the final kinetic energy 2 different ways and see if I get the same thing. Okay, so the kinetic energy final, which I called 1 over here, should be 1/2 mv1 squared. So that'd be a half times m. So now we do need the m, 75, times that last answer squared. 4725 joules. Okay, that should equal the initial potential plus the initial kinetic. So just on the calculator, we don't have to write this down. Let's check that. M times G times H. I think my H was 5, right? Yep, 5. Plus 1/2 M V squared. So times 16. The exact same thing. Okay. Yep, everything must be right. All right, now let's check and see what they got over here. Yeah, they put in scientific notation, same thing. And they're saying use projectile motion to check the answers. All right, I think that's a good place to stop.